Tonight, we're going to confront a question that seems so simple it almost feels childish, but when you actually try to answer it, it opens up one of the most elegant mysteries in all of physics. Why don't planets fall into the sun? Think about it. The sun's gravity is pulling on Earth right now. It's pulling on every planet in the solar system, every single second of every single day. Gravity never stops. It never takes a break. It never weakens to zero. So why hasn't Earth been dragged into the sun and destroyed billions of years ago? The answer is not what most people think. Planets don't resist gravity. They don't push back against it. They don't float. The truth is, Earth is falling toward the sun right now. It just keeps missing. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you already know, but probably haven't thought deeply about. Gravity. You experience it every single moment of your life. When you wake up in the morning and put your feet on the floor, gravity is pulling you down. When you pour coffee into a mug, gravity is pulling the liquid down. When you toss your keys onto the counter, gravity curves their path and brings them down. Everything falls, always, without exception. Gravity is the most familiar force in the universe. You've lived with it since the moment you were born. It's shaped your bones, your muscles, your sense of balance. It determines how high you can jump, how fast you fall, and how hard you land. It keeps the water in your glass, the air in the atmosphere, and the atmosphere on the planet. Gravity is constant. It doesn't turn off, it doesn't take breaks, it doesn't weaken to zero, no matter how far away you get from a massive object. It fades with distance, yes, but it never fully disappears. The gravitational pull of the sun reaches out across the entire solar system and beyond. It reaches past Neptune, past the Kuiper Belt, past the Oort cloud, and into interstellar space. Even at the edge of the sun's influence, trillions of miles away, its gravity is still there. Faint, incredibly faint, but still pulling. Still reaching, still pulling everything toward itself. Now, think about what that means for the planets. The sun is massive. It contains 99.86% of all the mass in the entire solar system. Everything else, every planet, every moon, every asteroid, every comet, every grain of dust floating between the worlds, all of that together makes up just 0.14% of the solar system's mass. The sun is the overwhelmingly dominant object in our cosmic neighborhood. Its gravitational pull is immense. At a distance of Earth about 93 million miles from the sun, the gravitational acceleration due to the sun is about 0.006 meters per second, squared. That might not sound like much compared to the 9.8 meters per second squared you feel standing on Earth's surface. But here is the critical thing. That pull never stops. It acts on Earth every second of every minute, of every hour, of every day, of every year. It has been pulling on Earth for 4.5 billion years without interruption. Not once in the entire history of our planet has the sun's gravity taken a break. Not once has it weakened to zero. Not once has it stopped reaching across those 93 million miles to tug on our world. So here is the question that should bother you. If the sun is constantly pulling Earth toward itself, why hasn't Earth fallen into the sun? Think about what happens when you hold a ball in your hand and let go. It falls straight down. Gravity pulls it toward the center of the Earth, and there is nothing to stop it except the ground. The ball doesn't hover, it doesn't drift sideways, it doesn't resist gravity, it just falls. If you drop a rock off a cliff, the same thing happens. The rock plummets downward, accelerating as it goes, pulled relentlessly by gravity until it hits the ground. Gravity pulls things toward the center of whatever massive object they're near. On Earth, that means things fall toward Earth's center. In the solar system, that means things should fall toward the sun. And that's exactly what would happen if you took Earth, held it still in space at 93 million miles from the sun, and simply let go. If Earth had no motion at all, if it were just sitting there motionless in space, gravity would pull it straight toward the sun. Earth would begin to accelerate, slowly at first, then faster and faster. It would pick up speed as it fell inward, drawn by the sun's relentless gravitational pull. After about 65 days, Earth would crash into the sun. 65 days. That's it. If our planet had no motion, no velocity, no momentum of any kind, it would take just over 2 months for the sun's gravity to drag it to fiery destruction. The entire planet, everything on it, every mountain and ocean and city and forest, all of it would be consumed, vaporized in the sun's 5,500 degree Celsius surface, long before reaching its 15 million degree Celsius core. This isn't a hypothetical scenario that requires some exotic physics to understand. This is just basic gravity. Drop something near a massive object, and it falls toward that object. That is what gravity does. It is all gravity does. Gravity pulls. It only pulls. It doesn't push. It doesn't hold things in place. It doesn't create barriers. Gravity is a one-trick force, and that one trick is pulling things together. So if gravity only pulls, and the sun's gravity is pulling on every planet in the solar system constantly, then there must be something preventing the planets from falling into the sun. There must be something else going on. Something that keeps Earth, Mars, Jupiter, and all the others from plunging into that enormous ball of nuclear fire at the center of our solar system. But let's think about what those 65 days would actually look like, because it paints a vivid picture of just how powerful the sun's gravity really is. In the first few days, you would notice nothing. The sun would look the same in the sky. The temperature on Earth's surface would be unchanged. Life would continue as normal. The acceleration at this stage would be almost imperceptible, just a slow drift inward across the vast gulf of 93 million miles. By the end of the first week, Earth would have moved roughly 500,000 miles closer. Still a tiny fraction of the total distance. The sun might look fractionally larger in the sky, but not enough for anyone to notice without precise instruments. But the thing about gravity is that it gets stronger as you get closer. As Earth drifts inward, the sun's pull increases. The acceleration builds. The fall gets faster. By the third week, Earth would be moving noticeably faster, covering millions of miles per day. The sun would begin to appear visibly larger. Temperatures on the daylight side would start to climb. By the fifth week, the sun would dominate the sky, noticeably bigger, noticeably hotter. The oceans would begin warming beyond anything in recorded climate history. By the sixth and seventh week, conditions would become catastrophic. The sun would loom enormous, a blazing disk growing larger by the hour. Surface temperatures would soar past anything life could endure. The oceans would begin to boil, not just on the surface, but all the way through. Vast plumes of steam rising into an atmosphere being stripped away by the intensifying solar wind. In the final days, Earth would be plunging inward at hundreds of kilometers per second. The sun would fill most of the visible sky, a wall of fire 5,500 degrees Celsius at the surface, and millions of degrees in the corona. Earth's rocky surface would begin to glow, then melt. The planet would be torn apart by tidal forces and vaporized long before it ever reached the sun's core. The entire planet, everything on it, every mountain and ocean and city and forest, all of it consumed, reduced to atoms in the sun's inferno. All of this in just 65 days. This isn't a hypothetical scenario that requires some exotic physics to understand. This is just basic gravity. Drop something near a massive object, and it falls toward that object. That is what gravity does. It is all gravity does. Gravity pulls. It only pulls. It doesn't push. It doesn't hold things in place. It doesn't create barriers. Gravity is a one-trick force, and that one trick is pulling things together. So if gravity only pulls, and the sun's gravity is pulling on every planet in the solar system constantly, then there must be something preventing the planets from falling into the sun. There must be something else going on. Something that keeps Earth, Mars, Jupiter, and all the others from plunging into that enormous ball of nuclear fire at the center of our solar system. Now, a lot of people have an intuitive answer to this question, and that intuitive answer is wrong. The most common misconception is that there is some kind of outward force pushing the planets away from the sun. People imagine gravity pulling inward and some other force pushing outward, and the planet sits at the point where these two forces balance. This sounds reasonable, and in everyday life, we encounter situations like this all the time. A book sitting on a table, for example, gravity pulls the book down, and the table pushes the book up. The forces balance, and the book stays still. So it seems natural to think something similar is happening with planets. Gravity pulls them toward the sun, and some outward force pushes them away, and the planet sits at the balance point between these two forces. But this is not what's happening. There is no outward force pushing planets away from the sun. None. Zero. If you could somehow measure all the forces acting on Earth right now, you would find exactly one significant force: the sun's gravity pulling Earth toward the sun. That's it. There is no counterforce, no repulsion, no invisible hand holding Earth at its current distance. The planets are not being held in place by a balance of forces. You might have heard the term centrifugal force and thought, that's the outward force keeping planets away from the sun. But centrifugal force is not a real force in the way gravity is a real force. It's what physicists call a fictitious force or a pseudo-force. It's a sensation you feel when you're in a rotating reference frame, like when you're in a car going around a curve and you feel pushed toward the outside of the curve, but nothing is actually pushing you outward. What's really happening is that your body wants to continue moving in a straight line, and the car is turning underneath you. Your body's tendency to keep moving in a straight line creates the sensation of being pushed outward, but there is no actual outward push. The same is true for planets. There is no centrifugal force pushing Earth away from the sun. There is only gravity pulling inward and Earth's own motion, which we will explore in detail very soon. But the key point right now is this. Do not think of a planet's orbit as a tug of war between two forces, one pulling in and one pushing out. That picture is wrong. There's only one force acting on a planet in orbit, and that force is gravity, and it points inward, toward the sun, always toward the sun. This is where most people get stuck. If there's no outward force, If the only force is gravity pulling inward, then how can the planet not fall in? What could possibly keep it up there if nothing is pushing it away? The answer lies in something that is not a force at all. It lies in motion. Specifically, it lies in a type of motion that Isaac Newton spent years thinking about, and that changed our understanding of the universe forever. But before we get to Newton, let's think about falling itself, because falling is more interesting than most people realize. When you drop a ball, it falls straight down. You know this. You've seen it 1,000 times. But why does it fall straight down? It fell straight down because it had no sideways motion when you released it. It was stationary in your hand, and when you let go, the only thing acting on it was gravity, pulling it straight toward the center of the Earth. So it went straight down. But what if the ball did have sideways motion when you released it? What if instead of just dropping it, you threw it horizontally? What happens then? You already know the answer from experience. The ball doesn't fall straight down. It curves. It moves forward and downward at the same time, tracing an arc through the air before hitting the ground. If you throw it gently, it curves quickly and hits the ground nearby. If you throw it hard, it travels farther before landing. But in every case, the ball is doing two things simultaneously. It's moving sideways because you gave it sideways motion, and it's falling downward because gravity is pulling it down. These two motions combine to create a curved path. The sideways motion doesn't fight gravity. It doesn't oppose gravity. It doesn't cancel gravity. Gravity is still pulling the ball down the entire time. The ball is still falling the entire time. But because the ball is also moving sideways, it doesn't fall straight down. It falls along a curve. This is an incredibly important concept. Motion to the side does not resist gravity. Gravity still does exactly what it always does. It still pulls the object downward. But if the object is also moving sideways, the result is a curved path rather than a straight plunge. The object falls, but it falls in a curve. Now, imagine throwing the ball harder. The harder you throw it, the farther it goes before hitting the ground. If you could throw it hard enough, something remarkable would start to happen. Earth is not flat. It's round. Its surface curves away from you in every direction. If you throw a ball fast enough, it falls toward the Earth, but the Earth's surface curves away beneath it. The ball is falling, but the ground is curving away, and if the ball is moving fast enough sideways, the rate at which it falls matches the rate at which the Earth's surface curves away. The ball keeps falling, but it never reaches the ground because the ground keeps curving away underneath it. Think about that carefully. The ball is falling. Gravity is pulling it downward. Nothing is pushing it up or outward. It is genuinely, truly falling toward the Earth. But it is also moving sideways so fast that the Earth's curvature means the ground drops away just as quickly as the ball drops toward it. The ball falls and falls and falls, and the ground curves and curves and curves, and the ball traces a path all the way around the planet and comes back to where it started. That is an orbit. An orbit is not floating. An orbit is not hovering. An orbit is not being held up by some mysterious force. An orbit is falling. Continuous, unending, perpetual falling. The object in orbit is falling toward the planet or star it orbits, every single moment, without interruption. But it is also moving sideways fast enough that it keeps missing. It falls toward the Earth, but the Earth's surface curves away. It falls toward the Sun, but the Sun is never quite where the planet is heading, because the planet's sideways motion carries it past. The planet is falling, but it's falling around the Sun rather than into it. This is the answer to our question. This is why planets don't fall into the sun. They do fall toward the sun. They are falling toward the sun right now, at this very moment. As you listen to these words, Earth is falling toward the sun. It has been falling toward the sun for 4.5 billion years. But Earth is also moving sideways at an enormous speed, about 30 kilometers per second, which is roughly 67,000 miles per hour. This sideways motion means that as Earth falls toward the sun, it simultaneously moves to the side. The sun's gravity curves Earth's path, bending it inward, but the sideways motion carries Earth forward, and the combination produces a smooth, continuous curve, a closed loop, an orbit. Earth doesn't resist gravity. It doesn't fight gravity. It doesn't push back against the sun's pull. It surrenders to gravity completely. It falls freely with no force opposing the fall. But because it has sideways motion, that free fall takes the shape of a curve rather than a straight line. The planet falls and falls and falls, endlessly circling the sun, perpetually missing it, tracing the same orbital path over and over again for billions of years. This is one of the most beautiful realizations in all of physics. The planets are not defying gravity. They are obeying it perfectly. Everything in orbit is in free fall. Every satellite circling the Earth, every moon circling a planet, every planet circling a star, every star circling the center of its galaxy, all of it is falling. All of it is in free fall. None of it is being held up, pushed out, or supported by anything. It is all falling, freely and continuously, in curved paths determined by gravity and sideways motion. Now, this raises an obvious question. Where did that sideways motion come from? Why are the planets moving sideways in the first place? If gravity only pulls things toward the sun, then how did the planets end up moving perpendicular to that pull? Why aren't they just falling straight in? The answer goes back to the very beginning, to the birth of the solar system itself, about 4.5 billion years ago. Before the sun existed, before the planets existed, there was a cloud, an enormous cloud of gas and dust floating in space, mostly hydrogen and helium, with traces of heavier elements created by older stars that had already lived and died. The cloud was vast, stretching across many light years. It was cold, dark, and diffused, with particles separated by enormous distances. But it wasn't perfectly still. Nothing in space is perfectly still. The cloud had a slight rotation. Maybe it was set spinning by a nearby supernova explosion. Maybe it inherited angular momentum from the larger galactic motions around it. Maybe it was just the random accumulation of tiny motions over millions of years. The exact cause doesn't matter. What matters is that the cloud was slowly, very slowly rotating. When part of this cloud began to collapse under its own gravity, something fascinating happened. As the cloud shrank, it spun faster. This is the same principle that makes a figure skater spin faster when they pull their arms in close to their body. It's called the conservation of angular momentum. When a rotating object gets smaller, it rotates faster. The total angular momentum stays the same, but since the object is now more compact, the speed of rotation increases to compensate. So as the cloud collapsed, it spun faster and faster. And because it was spinning, the material didn't all fall straight into the center. Instead, it flattened out into a disc. Think about spinning pizza dough. As you spin it, it flattens and stretches outward. The same basic principle applies here, though the physics is more complex. The collapsing cloud flattened into a rotating disk of gas and dust with a dense, hot center that eventually became the sun. This disk is called the protoplanetary disk, or sometimes the solar nebula. Everything in this disk was orbiting the young sun. Not because something placed it into orbit, but because the rotation that the original cloud had was preserved and amplified as the cloud collapsed. The material in the disk had sideways motion inherited from the original slow rotation of the cloud, and that sideways motion kept it from falling straight into the sun. Within this spinning disk, small clumps of matter began to stick together. Dust grains collided and merged, pebbles formed, rocks formed, boulders formed. Eventually these growing clumps became large enough that their own gravity started pulling in more material, accelerating their growth. Over millions of years, these clumps grew into planetesimals, then protoplanets, and finally into the planets we know today. And throughout this entire process, the sideways motion was preserved. The planets inherited their orbital velocity from the rotating disk of material that formed them. Every planet in the solar system moves in roughly the same direction around the sun. They all orbit counterclockwise when viewed from above the sun's north pole. They all orbit roughly in the same plane, the plane of the original disk. This is not a coincidence. It's a direct consequence of how they formed. They all came from the same rotating disk, so they all move in the same direction and in the same plane. This is where the sideways motion came from. It was not added later. It was not the result of some force pushing the planet sideways. It was built into the solar system from the very beginning, from the rotation of the original cloud of gas and dust. The planets were born moving sideways. They have been moving sideways ever since, and that sideways motion, combined with the sun's gravity pulling them inward, is what creates their orbits. Without the sideways motion, the planets would fall straight into the sun. Without gravity, the planets would fly off into space in straight lines. It is the combination of both, the inward pull of gravity and the sideways motion inherited from the solar system's formation, that produces the curved, closed paths we call orbits. Let's make sure this is absolutely clear, because this is the central insight of everything we're discussing tonight. Gravity does not hold planets in place. Gravity pulls planets inward. If gravity were the only thing acting, planets would crash into the sun. Sideways motion alone would not create an orbit either. Without gravity, a planet moving sideways would travel in a straight line forever, flying away from the sun into deep space. It is only when you have both gravity pulling inward and sideways motion carrying the planet forward that you get an orbit. The two combine to create a curved path. Gravity constantly bends the planet's path inward, while the planet's sideways motion constantly carries it forward. The result is a smooth, continuous curve that wraps all the way around the sun and connects back to itself. The planet traces this path endlessly, falling toward the sun but always missing, moving forward but always being pulled back. It's a perfect balance, not of forces, but of motion. The planet doesn't sit at a balance point between two opposing forces. It moves along a path that is shaped by one force, gravity, acting on a moving object. This is also why the phrase balance of forces is misleading when talking about orbits. There is no balance. There is only one force, and the planet is accelerating because of it. Acceleration doesn't always mean speeding up. In physics, acceleration means any change in velocity, including a change in direction. A planet in a circular orbit moves at a roughly constant speed, but its direction is constantly changing. It's always curving. That constant change in direction is acceleration, and it's caused by gravity. The planet is always accelerating toward the sun, always falling toward the sun. But because it's also moving sideways, that acceleration changes the planet's direction rather than simply increasing its speed toward the sun. The planet turns, curves, bends its path, falls inward, moves forward, turns again, curves again, over and over and over, billions of times. For billions of years. There is something deeply satisfying about this explanation. It's elegant. It doesn't require exotic forces or mysterious mechanisms. It requires only two things that we already understand: gravity, which pulls things together, and motion, which carries things forward. Combine the two, and you get orbits. You get planets circling stars, moons circling planets, stars circling galaxies. You get the entire structure of the cosmos, all from two simple ingredients. Gravity pulls things in, motion carries things forward. The universe does the rest. And the reason this works, the reason orbits are stable, the reason planets can fall toward the sun for billions of years without ever hitting it, is that in the vacuum of space, there is nothing to slow them down. There is no air resistance in space. There is no friction. There is nothing to gradually drain the sideways motion from a planet's orbit. On Earth, if you throw a ball, air resistance eventually slows it down and it hits the ground. But in space, there is no air. A planet moving at 30 kilometers per second will keep moving at roughly that speed indefinitely, because there is nothing to take that speed away. The sideways motion that the planets inherited from the formation of the solar system 4.5 billion years ago is still there, essentially unchanged. The planets are still moving sideways at nearly the same speed they had when they first formed. Gravity keeps pulling them inward, but their sideways speed never fades. And so the orbit continues, year after year, century after century, eon after eon. Earth has completed roughly 4.5 billion orbits around the sun, and it will complete billions more before the sun reaches the end of its life. All because of a simple combination of falling inward and moving sideways that began in a rotating cloud of gas and dust before our star even existed. Now that we understand the basic idea that planets are falling toward the sun while moving sideways fast enough to keep missing it, we need to go deeper. Because there is a question hiding inside this explanation that we haven't addressed yet. How fast is fast enough? If you throw a ball gently, it curves and hits the ground. If you throw it harder, it goes farther before landing. If you could throw it impossibly fast, it would circle the Earth and never land. But what is that critical speed? Is there a specific number, a precise velocity where falling toward the sun and moving sideways combine to create a stable orbit? The answer is yes, and the precision of that number is astonishing. Every orbit in the solar system exists because an object is moving at almost exactly the right speed for its distance from the sun. Too slow and it spirals inward. Too fast and it escapes into deep space. At just the right speed, it traces a closed path around the sun over and over again. This critical speed is called the orbital velocity, and it depends on two things: the mass of the object you're orbiting and how far away you are from it. The closer you are to a massive object, the stronger its gravitational pull, and the faster you need to move sideways to avoid falling in. The farther away you are, the weaker the pull, and the slower you need to move. For Earth, the orbital velocity works out to about 30 kilometers per second. That is roughly 67,000 miles per hour. Every hour of every day, Earth is hurtling through space at 67,000 miles per hour relative to the Sun. You don't feel this motion because everything around you, the ground, the air, the buildings, your coffee mug, is all moving at the same speed in the same direction. There is no wind from this motion because the atmosphere moves with the planet. There is no vibration because there is nothing in space for the planet to bump against. You are riding on a giant rock that is screaming through space at 30 kilometers per second, and you feel absolutely nothing. If Earth was slightly closer to the Sun, say at the distance of Venus, it would need to move faster to maintain an orbit, about 35 kilometers per second. If it were at the distance of Mars, it would need to move slower, about 24 kilometers per second. Mercury, the closest planet, orbits at about 47 kilometers per second. Neptune, far out in the cold reaches of the solar system, crawls along at just over 5 kilometers per second. Each planet moves at precisely the speed required for its distance from the Sun, not approximately, not roughly, precisely. If Earth's orbital speed suddenly dropped by just a few percent, our orbit would change. We would start falling closer to the Sun, sweeping inward before swinging back out in a more elongated path. If our speed increased by a few percent, we would move farther from the Sun before being pulled back. The orbital velocity for any given distance is not a suggestion. It is a requirement dictated by the laws of physics. Move at that speed, and you orbit. Move slower, and you fall inward. Move faster, and you climb outward. This relationship was not always understood. For most of human history, people had no idea why the planets moved the way they did. The ancient Greeks developed elaborate models involving perfect circles within circles, called epicycles, to try to predict planetary positions. These models work reasonably well for predicting where a planet would appear in the sky, but they didn't explain why planets moved that way. They were descriptions, not explanations. The planets just moved in circles because that's what planets do. The divine order demanded perfection, and circles were considered the most perfect shape. It wasn't until the early 1600s that a German mathematician named Johannes Kepler figured out something that overthrew 2,000 years of assumptions. Kepler had access to meticulous observations of planetary positions compiled by the Danish astronomer Tycho Brahe. Brahe had spent decades carefully measuring the positions of planets against the background stars with a precision that was extraordinary for his era. When Brahe died in 1601, Kepler inherited this treasure of data. And Kepler did something remarkable with it. He tried to fit the orbit of Mars to a perfect circle. He worked on this for years. He adjusted the center of the circle. He adjusted the speed at which Mars moved along the circle. He tried every trick he could think of, but no matter what he did, the circular orbit was always slightly off. The predictions from his circular model disagreed with Brahe's observations by about 8 arc minutes. An arc minute is 1/60th of a degree. It's tiny. Most people wouldn't notice it. Many astronomers at the time would have shrugged and called it close enough, but Kepler refused to ignore it. He trusted Brahe's data. He believed the observations were accurate. And if the data didn't fit a circle, then maybe the orbit wasn't a circle. After years of grueling calculations, all done by hand without computers or even a basic calculator, Kepler discovered the truth. The orbit of Mars is not a circle. It is an ellipse. An ellipse is like a stretched circle, an oval shape with 2 focal points instead of 1 center. And the Sun doesn't sit at the center of the ellipse. It sits at one of the two focal points, slightly off to the side. This was Kepler's first law of planetary motion, published in 1609. Planets orbit the Sun in ellipses with the Sun at one focus. This might sound like a minor geometric detail, but it was revolutionary. For 2,000 years, everyone assumed orbits were circles. Circles were perfect. Circles were divine. Circles were obvious. Kepler showed that nature doesn't care about human ideas of perfection. Orbits are ellipses, and the Sun is not at the center. The Sun is off to one side at a focal point. This means that planets don't stay at the same distance from the Sun throughout their orbit. There is a point where the planet is closest to the Sun, called perihelion, and a point where it is farthest, called aphelion. For Earth, the difference is relatively small. Earth's orbit is nearly circular, with a perihelion of about 91.5 million miles, and an aphelion of about 94.5 million miles. The difference is only about 3 million miles, roughly 3%. You wouldn't notice the change in the Sun's size with your naked eye. But for some planets, the difference is dramatic. Mars has a much more elliptical orbit. Its distance from the Sun varies by about 26 million miles between perihelion and aphelion. Mercury's orbit is the most elliptical of all the planets. Its distance from the Sun ranges from about 29 million miles at perihelion to about 43 million miles at aphelion. That is a huge difference, nearly 50% more distant at its farthest compared to its closest point. Kepler's second law describes how a planet moves along its elliptical orbit. A planet doesn't move at a constant speed. It speeds up when it's closer to the Sun and slows down when it's farther away. Specifically, Kepler found that an imaginary line drawn from the Sun to the planet sweeps out equal areas in equal times. This is the law of equal areas. When the planet is near perihelion, close to the Sun, it moves faster along its orbit. The line from the Sun to the planet sweeps through a short, wide sector. When the planet is near aphelion, far from the Sun, it moves more slowly, and the line sweeps through a long, narrow sector. But the area of both sectors is the same for any given time interval. This might sound abstract, but it captures something profound. A planet in an elliptical orbit is constantly trading speed for distance. When it falls closer to the Sun, it speeds up. When it climbs farther away, it slows down. But the total energy remains the same. The planet is not gaining or losing energy. It is simply converting between kinetic energy, the energy of motion, and potential energy, the energy of position in a gravitational field. When you're close to the Sun, you have lots of kinetic energy and less potential energy. When you're far from the Sun, you have less kinetic energy and more potential energy. The total always balances out. This is why elliptical orbits are stable. The planet isn't slowly losing energy on each orbit. It isn't gradually spiraling inward or drifting outward. The energy it gains falling toward the Sun on one half of its orbit is exactly returned as it climbs away from the Sun on the other half. The orbit repeats endlessly, with the planet tracing the same elliptical path over and over. Kepler's third law connects the size of an orbit to how long it takes to complete. The farther a planet is from the Sun, the longer its orbital period. But it's not a simple proportional relationship. Kepler found that the square of the orbital period is proportional to the cube of the average distance from the Sun. Mercury, closest to the Sun, takes only 88 Earth days to complete one orbit. Venus takes 225 days. Earth takes 365 and a quarter days. Mars takes 687 days. Jupiter, much farther out, takes about 12 Earth years. Saturn takes about 29 years. Uranus takes 84 years. Neptune takes 165 years. The pattern is clear: the farther you are, the longer your year. But the relationship is precise and mathematical, not just a general trend. Kepler discovered these three laws through sheer mathematical effort, working from Brahe's observations. But he didn't know why these laws were true. He couldn't explain the underlying reason. The laws were descriptions of how planets moved, but not explanations of why they moved that way. Why ellipses? Why equal areas in equal times? Why the specific relationship between distance and period? Kepler could describe the motion but couldn't explain the cause. That explanation came about 80 years later from Isaac Newton. Newton's great insight was the law of universal gravitation, published in 1687 in his masterwork, the Principia Mathematica. Newton proposed that every object in the universe attracts every other object with a force that depends on their masses and the distance between them. The force is proportional to the product of the two masses and inversely proportional to the square of the distance between them. This is the inverse square law. If you double the distance between two objects, the gravitational force drops to 1/4. If you triple the distance, it drops to 1/9. If you move 10 times farther away, the force is 1/100th as strong. This single law, combined with Newton's laws of motion, explained everything. It explained why planets orbit in ellipses. It explained why they speed up near the sun and slow down far from it. It explained the precise mathematical relationship between orbital distance and period. It explained the tides. It explained the shape of the Earth, slightly flattened at the poles because of its rotation. It explained the precession of Earth's axis. It explained the orbits of comets. It explained the motion of the moon. All of Kepler's laws, which had been discovered empirically through painstaking observation and calculation, fell out naturally from Newton's single gravitational equation. This was one of the greatest intellectual achievements in human history. One equation explained the motion of every object in the solar system. The universe, it turned out, was not governed by divine whim or inscrutable complexity. It was governed by precise mathematical laws that could be written on a single line. Newton also formalized the concept we discussed earlier, the idea that an orbit is a form of continuous falling. In the Principia, Newton described a thought experiment that has become one of the most famous in the history of science. Imagine a cannon on top of a very tall mountain, so tall that it extends above the atmosphere. Fire the cannon horizontally. The cannonball flies forward and falls, hitting the ground some distance away. Now fire it with more gunpowder. The ball goes farther before landing. Fire it with even more. It goes even further. At some critical speed, the cannonball is moving forward so fast that as it falls toward Earth, the Earth's curved surface drops away beneath it at exactly the same rate. The cannonball falls and falls but never reaches the ground. It circles the entire planet and comes back to the mountaintop. It is in orbit. This thought experiment perfectly captures the physics of orbital motion. The cannonball is falling the entire time. Gravity never stops pulling it toward Earth, but the sideways speed is enough that the curved ground keeps retreating. Falling plus sideways motion equals an orbit. Newton even drew a diagram of this in the Principia. It shows the mountain, the cannon, and several trajectories with increasing initial speed. The slower shots curve and hit the ground. The faster ones go farther before landing. And at just the right speed, the shot goes all the way around. It is one of the most elegant diagrams in all of science. Newton's framework reigned supreme for over 2 centuries. It predicted planetary positions with extraordinary accuracy. It was used to discover new planets. One of the earliest and most dramatic confirmations of Newton's theory came from Edmund Halley, a contemporary and friend of Newton. Halley used Newton's gravitational equations to study the records of comets observed throughout history. He noticed that comets seen in 1531, 1607, and 1682 appeared to follow remarkably similar paths through the sky. Halley proposed they were the same comet returning on a regular orbit, and predicted it would return again in 1758. Halley died in 1742, 16 years before his prediction could be tested. But in 1758, right on schedule, the comet appeared exactly as Halley had calculated. It was named Halley's Comet in his honor. Newton's gravitational theory had predicted the return of a celestial visitor decades in advance, vindicating both Newton's physics and Halley's faith in it. But Newton's theory wasn't perfect. There was one small problem that wouldn't go away: the orbit of Mercury. Mercury's orbit precesses, which means its elliptical path slowly rotates around the Sun. This precession was known and mostly explained by the gravitational tugs of the other planets. But when astronomers carefully accounted for all the known influences, there was still a tiny unexplained shift. Mercury's perihelion, the point where it is closest to the Sun, was advancing by about 43 arcseconds per century, more than Newton's theory predicted. 43 arcseconds per century. That is an incredibly tiny amount. You would never notice it with the naked eye. It would take thousands of years for the shift to become visible without precision instruments. But it was there, consistently, stubbornly refusing to match Newton's predictions. For decades, astronomers searched for explanations within Newton's framework. Some proposed a hidden planet called Vulcan orbiting closer to the Sun than Mercury. Others suggested the Sun wasn't perfectly spherical, and the extra mass at its equator was causing the shift. None of these explanations worked. The answer came from Albert Einstein in 1915, when he published his general theory of relativity. Einstein didn't just tweak Newton's theory, he replaced it with a fundamentally different way of understanding gravity. In Newton's view, gravity was a force, a mysterious action at a distance where massive objects pull on each other across empty space. Newton himself was uncomfortable with this idea. He famously wrote that the idea of one body acting on another through empty space without any intermediary was so absurd that no person with a competent faculty of thinking could ever accept it. But his equations worked so well that people used them anyway, and tried not to think too hard about the mechanism. Einstein resolved this mystery by proposing that gravity isn't a force at all. Instead, massive objects curve the fabric of space-time itself, and other objects move along these curves. Imagine placing a heavy bowling ball on a stretched rubber sheet. The ball creates a depression, a curve in the sheet. Now roll a marble across the sheet. The marble doesn't travel in a straight line. It curves toward the bowling ball. Following the depression in the sheet, it looks like the bowling ball is attracting the marble, but nothing is pulling the marble. The marble is simply following the curved surface. This is a simplified analogy, and it has limitations because real space-time is four-dimensional and the Curvature works differently than a two-dimensional rubber sheet, but it captures the essential idea. The sun curves space-time around it. The planets move through this curved space-time, following paths called geodesics, which are the straightest possible paths through curved space. In flat space, the straightest path is a straight line. In curved space around the sun, the straightest path is an ellipse. The planets are moving as straight as they possibly can through the curved space-time created by the sun's mass. They don't feel any force. They are in free fall, moving along the natural contours of space itself. This is why astronauts in orbit feel weightless. It's not because they're far from Earth. The International Space Station orbits at an altitude of only about 400 kilometers. At that altitude, gravity is about 90% as strong as it is on Earth's surface. The astronauts absolutely have gravity acting on them. But they feel weightless because they and the station are all falling together. They're in free fall, following the curved space-time around Earth. There is no force pushing them against the floor. There is no force pushing them in any direction. They're just falling, freely, and everything around them is falling at the same rate. This is the same physics that governs planetary orbits. Planets are in free fall through curved space-time. They don't feel any force. If you were somehow riding on the surface of a planet and could only feel forces acting on you, you wouldn't feel the sun's gravity pulling you. You would feel weightless in the direction of the sun because you and the planet are falling together. You only feel the planet's own gravity pulling you toward its surface. The sun's gravity doesn't create a sensation of being pulled. It creates a curved path through space that the planet follows naturally. Einstein's general relativity also solved the Mercury problem. In general relativity, the curvature of space-time near the sun is slightly different from what Newton's theory predicts. The difference is tiny, only significant very close to the sun where gravity is strongest. Mercury, being the closest planet, experiences this difference more than any other planet. And when Einstein calculated Mercury's orbit using general relativity, the extra 43 arcseconds per century of precession fell out naturally. No hidden planet, no misshapen sun, just a more accurate understanding of how gravity works. This was one of the first great confirmations of general relativity, and it cemented Einstein's theory as the definitive description of gravity. Newton's theory is still incredibly useful. For most purposes, it gives answers that are indistinguishable from general relativity. Engineers use Newton's equations to plan spacecraft trajectories because the calculations are simpler and the answers are accurate enough. But for extreme situations, near massive objects or at very high speeds, general relativity is necessary. And for understanding the true nature of orbits, for understanding what is really happening when a planet circles a star, Einstein's picture is more complete. Planets don't orbit because a force is pulling them while they resist. Planets orbit because space-time is curved, and they are following the natural contours of that curvature while moving through it with the velocity they inherited from the formation of the solar system. There is one more concept we need to explore before we move on, and that is escape velocity. We've talked about the orbital velocity, the speed needed to maintain a stable orbit at a given distance, but what happens if something is moving even faster? If you keep increasing the sideways speed of an object, its orbit becomes more and more elongated. A gentle increase makes the orbit slightly more elliptical. A larger increase creates a very stretched out ellipse that takes the object far from the sun before gravity pulls it back. But there is a threshold, a specific speed at which the orbit stops being a closed ellipse and becomes an open curve. The object moves so fast that it has enough energy to escape the gravitational pull entirely. It will slow down as it climbs away from the sun, but it will never slow down enough to be pulled back. It will keep moving outward forever, getting slower and slower but never stopping, never returning. This threshold is the escape velocity. At Earth's distance from the sun, the escape velocity from the solar system is about 42 kilometers per second. Earth moves at about 30 kilometers per second. So we are well below the escape velocity. We are gravitationally bound to the sun. We cannot escape without additional energy. If something gave Earth a sudden boost to 42 kilometers per second, our planet would leave the solar system entirely. It would fly off into interstellar space, never to orbit the sun again. The escape velocity, like the orbital velocity, depends on distance. Closer to the sun, you need more speed to escape because gravity is stronger. Farther away, you need less. And the escape velocity is always exactly the square root of 2 times the orbital velocity at any given distance. This is not a coincidence. It's a mathematical consequence of the inverse square law of gravity. Below the orbital velocity, you fall inward. At the orbital velocity, you orbit. Above the escape velocity, you leave. Between the orbital velocity and the escape velocity, you orbit in an increasingly elongated ellipse. The solar system is full of objects at different speeds relative to these thresholds. The planets all orbit at speeds close to the circular orbital velocity for their distances. Most asteroids do too, but some objects, like certain comets from the Oort cloud, fall inward on highly elongated elliptical orbits that take them close to the sun and then far out to the edges of the solar system. And occasionally, an object from interstellar space passes through the solar system on a hyperbolic trajectory, moving faster than escape velocity, never to return. In 2017, astronomers detected such an object for the first time. They named it Oumuamua, a Hawaiian word meaning scout or messenger. It entered the solar system from interstellar space, swooped past the sun, and flew back out. Its speed was too great for the sun's gravity to capture it. It was just passing through, a visitor from another star system, following the curves of space-time through our neighborhood and continuing on its way. This was a vivid demonstration that escape velocity is real and consequential. Below it, you're trapped. Above it, you're free. The planets are trapped. They have been falling around the sun for billions of years, and will continue for billions more. Their speeds are too low to escape, but perfectly suited to orbit. This arrangement is not precarious. It is not delicate. It is extraordinarily stable. The vacuum of space provides no friction, no drag, no resistance to drain the planet's sideways motion. Once an orbit is established in the emptiness of space, it persists. Gravity provides the centripetal acceleration that curves the path. The planet's motion provides the sideways component that prevents a direct plunge, and the absence of friction ensures that the energy of the orbit is conserved indefinitely. Kepler described the shapes. Newton explained the force. Einstein revealed the geometry. And together, their insights show us that planetary orbits are not a mystery or a miracle. They are the inevitable consequence of mass curving spacetime and objects moving through that curved spacetime with the velocity they were born with, falling forever in paths that close upon themselves, endlessly, beautifully, with a precision that has persisted for billions of years and will persist for billions more. But understanding how orbits work raises a harder question. Why are these orbits so stable? Why have they lasted billions of years without falling apart? The solar system is 4.5 billion years old. Earth has completed roughly 4.5 billion trips around the Sun. Mercury has completed nearly 19 billion orbits. Neptune, slow and distant, takes about 165 Earth years to complete a single trip around the Sun. In a human lifetime, Neptune barely moves through a fraction of its orbit. It has completed roughly 27 million orbits since the solar system formed, which sounds like a lot until you compare it to Mercury's 19 billion. But all of them are still orbiting. None of them has crashed into the Sun. None of them has drifted away into space. The orbits have been maintained for an almost incomprehensible span of time. How? What makes them so remarkably persistent? The answer begins with something that seems almost too simple. Space is empty. Not just a little empty. Profoundly, overwhelmingly empty. When you throw a ball on Earth, it eventually stops. Not because gravity stops pulling it, but because other forces act against its motion. Air resistance pushes back against the ball as it moves through the atmosphere. Friction slows it when it rolls along the ground. Every time the ball bounces, some of its energy is converted to heat and sound. Gradually, all the ball's kinetic energy is drained away and it comes to rest. This is our everyday experience with motion. Things slow down, things stop. Motion doesn't persist on its own. You have to keep pushing something to keep it moving. But this everyday intuition is wrong. It's an artifact of living on a planet with an atmosphere, with surfaces, with friction everywhere. In the absence of these things, in the vacuum of space, motion does persist. This is Newton's first law. An object in motion stays in motion at the same speed and in the same direction unless acted upon by an external force. On Earth, there are always external forces. Air resistance, friction, drag. But in space, there is essentially nothing. The space between planets is not perfectly empty. There are a few atoms per cubic centimeter of interplanetary space, mostly hydrogen, along with some dust grains. But this is so sparse that it has virtually no effect on a planet's motion. The density of the interplanetary medium is roughly 100 billion times less dense than Earth's atmosphere at sea level. For all practical purposes, the planets move through nothing. There is no air resistance in space, no friction, no drag, nothing to slow the planets down. The sideways velocity that the planets inherited from the protoplanetary disk 4.5 billion years ago has been essentially unchanged since then. Earth is still moving at about 30 kilometers per second, the same speed it has maintained for its entire existence. That speed hasn't decreased by any meaningful amount over 4.5 billion years because there is nothing in space to decrease it. This is profoundly different from our experience on Earth, and it's why orbital stability is so counterintuitive for most people. We're used to things slowing down. We're used to motion being temporary. We instinctively expect that anything moving must eventually stop. So when someone tells us that planets have been orbiting for billions of years, our gut reaction is that something must be sustaining that motion. Something must be providing energy. Something must be pushing the planets to keep them going. But nothing is. The planets are coasting. They've been coasting since the solar system formed. No engine drives them. No force pushes them forward along their orbits. They simply move because they have always been moving, and nothing has ever stopped them. Gravity doesn't slow them down. Gravity changes their direction, curving their paths into orbits, but it doesn't drain their energy. a planet in a perfectly elliptical orbit has the same total energy at every point in its orbit. When it falls closer to the Sun, it speeds up. It gains kinetic energy, but it loses gravitational potential energy by exactly the same amount. When it climbs away from the Sun, it slows down, losing kinetic energy, but it gains back gravitational potential energy. The total kinetic plus potential remains constant. This is the conservation of energy, and it is one of the most fundamental principles in all of physics. Energy is not created or destroyed. It can change form, but the total amount stays the same. In a frictionless environment like space, this means the energy of an orbit is permanent. The planet will keep orbiting at the same energy level forever unless something external adds or removes energy. Now, this raises an interesting comparison that helps clarify why planetary orbits are stable, but some other orbits are not. Consider the International Space Station. The ISS orbits Earth at an altitude of about 400 kilometers. At that altitude, it's above most of the atmosphere, but not all of it. There are still traces of atmosphere up there. Incredibly thin, but present. These few remaining air molecules create a tiny amount of drag on the station. Each molecule that bumps against the station takes away a tiny fraction of the station's kinetic energy. Individually, each collision is negligible, but collectively, over days and weeks and months, this drag adds up. The station slowly loses energy. As it loses energy, its orbit decays. It gradually drops lower, and as it drops lower, it encounters denser atmosphere, which increases the drag, which makes it lose energy faster, which makes it drop lower even more quickly. Left unchecked, the ISS would eventually slow down so much that it would re-enter the atmosphere and burn up. This is why the station needs periodic boosts. Visiting spacecraft fire their engines while docked to the station, pushing it back to a higher orbit, restoring the energy lost to atmospheric drag. Without these boosts, the station would deorbit within a few years. This is exactly what does not happen to planets. Earth orbits at 93 million miles from the Sun. At that distance, there is no atmosphere. There is no drag. There is nothing to slowly bleed away Earth's orbital energy. The contrast with the space station is instructive. The station orbits just barely above the atmosphere and slowly loses energy because of drag. Earth orbits in the deep vacuum of interplanetary space and loses essentially no energy at all. This is the key to orbital stability. Not some special mechanism that sustains the orbit, but the absence of any mechanism that would degrade it. Orbits persist because nothing disrupts them. The vacuum of space is the ultimate frictionless environment, and in a frictionless environment, motion persists forever. But wait, is space truly frictionless for planetary orbits? Are there no forces at all that could slowly change a planet's orbit over time? The answer is that there are some effects, but they are extraordinarily small. The planets exert gravitational tugs on each other. Jupiter, the most massive planet, tugs on every other planet in the solar system. These tugs cause small perturbations in the orbits. Over millions of years, these perturbations can accumulate, causing slow changes in the shapes and orientations of the orbits. This is why the orbits of the planets are not perfectly fixed ellipses. They evolve slowly over time, their eccentricities changing, their orbital planes tilting slightly, their perihelion points shifting. Earth's orbit, for example, cycles through periods of being more circular and more elliptical over timescales of about 100,000 years. These cycles are called Milankovitch cycles, named after the Serbian scientist Milutin Milankovic, who proposed in the early 20th century that these orbital variations influence Earth's climate. And he was right. The ice ages that Earth has experienced over the past few million years are closely correlated with these orbital cycles. When Earth's orbit is more elliptical, when its axial tilt is greater, when the timing of its closest approach to the Sun shifts relative to the seasons, the amount and distribution of sunlight reaching Earth's surface change. These changes can trigger or end ice ages. So the gravitational perturbations from other planets do have effects, but they don't destabilize the orbits. They cause slow, cyclic changes in orbital parameters, but they don't cause planets to crash into the Sun or fly out of the solar system. The perturbations are small enough that the orbits remain bounded. The planets wobble slightly, their orbits shifting and breathing over millions of years, but they stay in orbit. The precision of these gravitational interactions led to one of the most stunning predictions in the history of science. A prediction that demonstrated just how reliable orbital mechanics truly are. In 1781, the astronomer William Herschel discovered Uranus, the first planet found using a telescope. It was a momentous discovery. For as long as humans had watched the sky, there had been 5 known planets beyond Earth: Mercury, Venus, Mars, Jupiter, and Saturn. The discovery of a 7th planet expanded the known solar system overnight. Astronomers immediately set about tracking Uranus, measuring its position night after night, year after year, mapping its orbit with precision. But as decades of observations accumulated, something troubling emerged. Uranus was not where it was supposed to be. Its observed position didn't quite match the orbit predicted by Newton's law of gravitation, even after accounting for the gravitational tugs of Jupiter and Saturn. The discrepancy was small but persistent. By the 1830s and 1840s, the difference between the predicted and observed positions had grown to about 2 arc minutes. That is a tiny angle, roughly 1/15th the apparent width of the full moon. Most people would never notice such a small deviation, but astronomers noticed, and it bothered them. Newton's laws had proven so spectacularly accurate for every other planet that a discrepancy for Uranus suggested something important was being missed. 2 mathematicians working independently tackled the problem. In France, Urbain Le Verrier spent months performing extraordinarily complex calculations, all by hand, working backward from the discrepancies in Uranus's orbit to determine where an unseen planet must be lurking and how massive it must be to produce the observed perturbations. In England, John Couch Adams performed a similar analysis, arriving at a similar conclusion. Both predicted that an undiscovered planet existed beyond Uranus, and both calculated approximately where in the sky that planet should be found. On the 23rd of September, 1846, the German astronomer Johann Galle pointed his telescope at the position Le Verrier had specified. Within an hour of beginning his search, he found the planet. It was within 1 degree of the predicted position. 1 degree in a sky that stretches 360 degrees around you. Le Verrier had told astronomers almost exactly where to look, and there it was. The planet was named Neptune. The discovery of Neptune was one of the greatest triumphs of mathematical physics. A planet had been discovered not by looking through a telescope and stumbling upon it, but by noticing that another planet's orbit was slightly off, calculating what must be causing the discrepancy, and predicting exactly where to find the answer. The laws of orbital mechanics, Newton's equations describing how gravity and motion produce orbits, were so precise that they could reveal the existence of an invisible object billions of miles away through nothing but mathematics. Gravity's fingerprints were written into the motion of Uranus, and mathematicians read those fingerprints and found a world. This episode demonstrates something profound about the reliability of orbits. Planetary motions are not approximate. They are not rough tendencies. They are precise, mathematically exact paths governed by laws that operate with extraordinary fidelity. The tiny wobble in Uranus's orbit, a deviation of 2 arc minutes over decades, was not noise or error. It was a signal, a precise gravitational signature left by an unseen world, and the laws of orbital mechanics were accurate enough to decode that signal and point directly to the source. There is another effect that is even smaller than planetary perturbations but fascinating. As the sun radiates light and loses mass through the solar wind, its gravitational pull very slowly weakens. Over billions of years, this causes the planets to very gradually drift outward. The effect is incredibly tiny. The sun loses about 4.3 million metric tons of mass every second through the conversion of hydrogen to helium and the energy released as sunlight, and another 1 to 2 million metric tons per second through the solar wind. That sounds like a lot, but compared to the sun's total mass of about 2 times 10 to the 30th kilograms, it's almost nothing. Over the entire 4.5 billion year history of the solar system, the sun has lost only about 0.03% of its total mass. Earth's orbit has expanded by roughly the same fraction, a tiny amount, not enough to notice without extremely precise measurements. There's also the effect of gravitational radiation. General relativity predicts that orbiting objects emit gravitational waves, ripples in space-time that carry energy away from the system. As energy is radiated away, the orbit should slowly shrink. But for planetary orbits, this effect is absurdly small. Earth's orbit shrinks due to gravitational radiation by a fraction of a nanometer per century, a distance smaller than an atom. Even over timescales trillions of times longer than the current age of the universe, this effect would produce no meaningful change in Earth's orbit. For all practical purposes, planetary orbits in our solar system are permanent. They will last for billions of years more, until the sun itself dies and transforms into a red giant, swallowing the inner planets and disrupting the outer ones. This stability is not unique to our solar system. Across the universe, wherever you find a star with planets, you find the same remarkable persistence. Orbits established billions of years ago continue today, maintained by the same simple combination of gravity and inertial motion in the vacuum of space. There is nothing exotic about orbital stability. It is simply what happens when you have a moving object in a gravitational field with nothing to slow it down. The orbit sustains itself, not through any active mechanism, but through the passive absence of disruption. Let me address another common misconception that often arises at this point. Some people think that orbits require a perfect balance that could easily be disrupted. They imagine the planets walking a tightrope, where the slightest nudge would send them crashing into the sun or flying into space. This is not accurate. Orbits are actually quite robust. If you nudged Earth, giving it a small push toward the sun, it wouldn't spiral in and crash. Instead, its orbit would change slightly. It would adopt a new elliptical orbit that brings us slightly closer to the sun at perihelion and slightly farther at aphelion. The new orbit would be different from the old one, but it would still be an orbit. The planet would still go around the sun. It wouldn't crash. Similarly, if you gave Earth a small push away from the sun, it would adopt a slightly larger orbit. It still wouldn't escape. It would just orbit at a slightly greater average distance. To actually make a planet crash into the sun, you would need to remove almost all of its sideways velocity. You would need to slow Earth down from 30 kilometers per second to nearly zero. That would require an enormous amount of energy, far more than any natural process in the solar system could provide. And to make a planet escape the solar system, you would need to speed it up to escape velocity, about 42 kilometers per second at Earth's distance. Again, an enormous change. Small perturbations don't destroy orbits. They modify them. The planet shifts to a slightly different elliptical path, but it keeps orbiting. This is why the gravitational tugs from other planets don't destabilize the solar system. They change the orbits slightly, but the orbits remain orbits. However, this stability has limits. Over extremely long timescales, the cumulative effect of gravitational perturbations can become significant. In the 1980s and 90s, mathematical physicists began using powerful computers to simulate the solar system's evolution over billions of years. These simulations revealed something surprising. The solar system is not perfectly stable forever. It is chaotic. Not chaotic in the everyday sense of random and unpredictable, but chaotic in the mathematical sense. Small differences in initial conditions can lead to very different outcomes over long timescales. Jacques Lascar, a French astronomer, published groundbreaking work showing that the orbits of the inner planets, Mercury, Venus, Earth, and Mars, are chaotic over timescales of tens of millions of years. This means that while we can predict their positions quite accurately for the next few million years, beyond that, our predictions become increasingly uncertain. Over billions of years, there's a small but real probability that Mercury's orbit could become so eccentric that it crosses Venus's orbit, potentially leading to a collision or ejection from the solar system. Simulations suggest this probability is about 1% over the next 5 billion years before the sun becomes a red giant. 1% over 5 billion years. These are not immediate concerns. The solar system is stable enough for life to have existed on Earth for nearly 4 billion years without any planetary catastrophe. The chaos is extremely slow, operating over timescales vastly longer than human civilization. But it does mean that the solar system's orbital arrangement is not guaranteed to last forever. Given enough time, the delicate gravitational dance between the planets could eventually produce dramatic changes. This brings us to a broader point about orbits throughout the universe. Not all orbits last forever. Some don't last very long at all. The universe is full of examples of orbits that fail, of objects that do fall into the thing they're orbiting, or that are ejected into space. These examples help us understand what makes planetary orbits special and why they've survived so long. Comets provide a vivid example of what happens when an orbit brings an object dangerously close to a massive body. Long-period comets from the Oort cloud can have orbits that bring them extremely close to the sun. When a comet approaches the sun, the intense heat vaporizes its icy surface, creating the spectacular tail that makes comets so beautiful. But this process also destroys the comet. Each pass near the sun strips away more material. Some comets survive many passages, slowly shrinking over thousands or millions of years. Others don't survive at all. In 1994, Comet Shoemaker-Levy 9 provided a dramatic demonstration of orbital failure. This comet had been captured by Jupiter's gravity and was orbiting the giant planet, but its orbit was not stable. Tidal forces from Jupiter, the difference in gravitational pull between the near side and far side of the comet, tore it apart into a chain of fragments. Those fragments then crashed into Jupiter one by one, producing enormous impact scars in Jupiter's atmosphere, some larger than Earth. Shoemaker-Levy 9 had the sideways motion to orbit Jupiter, but its orbit brought it too close. The tidal forces exceeded the comet's structural integrity, and it was torn apart and absorbed. This is what happens when an orbit takes you too close to a massive body. If your structural integrity can't withstand the tidal forces, you break apart. Stars can suffer the same fate. Near the supermassive black holes at the centers of galaxies, stars sometimes wander onto orbits that bring them too close. When a star passes within a certain distance of a black hole, the tidal forces can exceed the star's self-gravity, tearing the star apart in what astronomers call a tidal disruption event. The star's material stretches into a long stream that spirals around the black hole, heating up to millions of degrees and producing a brilliant flare of radiation. These events have been observed in distant galaxies. They are spectacular and violent, a stark reminder of what happens when an orbit fails, when an object's path brings it within the destructive reach of an overwhelmingly massive body. The key difference between these failed orbits and the stable orbits of planets in our solar system is distance. The planets orbit at safe distances from the Sun. They never get close enough for tidal forces to threaten them. Their orbits are nearly circular, with relatively small variations in distance from the Sun. They don't plunge inward on highly eccentric paths that bring them dangerously close. And the vacuum of space ensures their orbital energy is not drained away by friction or drag. But there is one more way that orbits can fail, and it is perhaps the most spectacular of all. It involves gravitational waves. The ripples in spacetime predicted by Einstein's general relativity. When two massive objects orbit each other closely, they emit gravitational waves. These waves carry energy away from the system. As energy is lost, the orbit shrinks. The objects spiral closer together, orbiting faster and emitting even more gravitational waves, losing energy even faster. It is a runaway process. The orbit decays, slowly at first, then faster and faster, until the two objects finally merge. For ordinary planetary orbits, this process is negligible. As I mentioned earlier, Earth's orbit shrinks by a fraction of a nanometer per century due to gravitational radiation. That is beyond negligible, but for compact, massive objects orbiting very close together, the effect becomes dramatic. Binary neutron stars, for example, are pairs of neutron stars orbiting each other at close range. A neutron star is the collapsed remnant of a massive star that has exploded as a supernova. It contains roughly 1.5 times the mass of the Sun, compressed into a sphere only about 12 miles across. The density is almost beyond comprehension. A teaspoon of neutron star material would weigh about 4 billion metric tons on Earth. When two neutron stars orbit each other closely, they emit powerful gravitational waves. The energy loss causes their orbit to shrink. Over millions of years, the neutron stars spiral closer and closer together, orbiting faster and faster, until they finally collide and merge in a cataclysmic event that produces a burst of gravitational waves so powerful that it can be detected by instruments on Earth billions of light years away. This is exactly what the LIGO Observatory detected in August of 2017. Two neutron stars, each about 1.5 times the mass of the Sun, are spiraling together and merging about 130 million light-years away. The event produced gravitational waves that were detected by LIGO and Virgo, and it was also observed by telescopes across the electromagnetic spectrum, from gamma rays to radio waves. It was the first time a gravitational wave event was observed in both gravitational waves and light, confirming Einstein's predictions in spectacular fashion. This is an orbit that failed. Two objects fell toward each other, spiraling inward, losing energy to gravitational waves until they finally crashed together. It is the ultimate fate of any binary system that loses energy over time. But it takes an extraordinarily long time for this to happen in most cases. The two neutron stars detected by LIGO had been spiraling toward each other for hundreds of millions of years before they finally merged. For planetary orbits in our solar system, the timescale is incomprehensibly longer. Earth's orbit would need far longer than the current age of the universe to decay through gravitational wave emission. It simply isn't going to happen. So, to summarize the stability of planetary orbits, the planets are stable because they move through a nearly perfect vacuum where nothing drains their energy. Their sideways velocity, inherited from the rotating disk of gas and dust that form the solar system, has been preserved almost unchanged for 4.5 billion years. Gravity curves their paths into ellipses, but it doesn't remove energy from the system. The conservation of energy ensures that the total energy of each orbit remains constant. Small perturbations from other planets modify the orbit slightly, but don't destroy them. Gravitational wave emission is negligible for planetary orbits. And the chaotic behavior of the inner planets operates on timescales of billions of years, long enough that the solar system has remained essentially stable for its entire history. The result is a solar system that looks almost frozen in place from a human perspective. The planets trace the same paths year after year, century after century, millennium after millennium. The sunrise happens every morning, not because some divine mechanism ensures it, but because Earth's orbit is so stable that its motion is essentially unchanging on human timescales. The seasons repeat because Earth's axial tilt and orbital path are stable. The calendar works because the orbital period is constant. The predictability of the cosmos, the ability to know where the sun will rise tomorrow and when the next eclipse will occur, and what the sky will look like 1,000 years from now, all of this rests on the remarkable stability of orbits in the vacuum of space. Gravity pulls, motion carries forward, nothing slows things down, and so the dance continues, precise and unwavering as it has for billions of years, and as it will for billions more. This is not a delicate arrangement, it is a robust one, built not on balance, but on the simple, elegant physics of falling through empty space with nowhere else to go. But this mechanism, falling sideways fast enough to keep missing, is not unique to our solar system. It is not a special arrangement that applies only here. It is the universal principle behind nearly every large-scale motion in the cosmos. Everywhere you look, from the smallest moons to the largest galaxies, you find the same thing. Objects falling toward each other, moving sideways, tracing curved paths through space-time. The entire universe is in free fall, and once you see it, you cannot unsee it. Start with the moon. The moon orbits Earth at an average distance of about 384,400 kilometers. It moves at roughly 1 kilometer per second, which is slow compared to Earth's 30 kilometers per second around the Sun, but perfectly matched to the weaker gravitational pull of Earth compared to the Sun. The moon is falling toward Earth, right now, constantly, the same way Earth is falling toward the Sun. Gravity pulls the moon toward Earth every second of every day. But the moon is also moving sideways, and that sideways motion means it keeps missing Earth, tracing a roughly elliptical path around our planet once every 27.3 days. Isaac Newton himself made this connection explicit. In fact, it was the moon that helped Newton realize the true nature of gravity in the first place. The famous story, perhaps exaggerated but rooted in truth, is that Newton saw an apple fall from a tree and wondered if the same force that pulled the apple toward the ground also pulled the moon toward the Earth. He calculated the gravitational acceleration at the moon's distance, accounting for the inverse square law, and found that it matched perfectly with the moon's observed orbital motion. The force pulling the apple straight down and the force curving the moon's path were the same force. Gravity. The apple fell straight down because it had no significant sideways motion. The moon fell in a curve because it had sideways motion, same force, different result, because of motion. This was a staggering realization. Before Newton, people thought of celestial motion and terrestrial motion as fundamentally different things. The heavens operated by different rules than the Earth. Aristotle had taught that objects in the heavens moved in perfect circles because that was their natural state, while objects on Earth moved in straight lines toward the ground. These were considered completely separate types of motion, governed by completely different principles. Newton unified them. He showed that the same gravity that makes an apple fall also makes the moon orbit. The same gravity that pulls you toward Earth's surface also holds the planets in their paths around the sun. There is one gravity, one law, one principle operating everywhere in the universe. The difference between an apple falling and the moon orbiting is not a difference in the force acting on them. It is a difference in their sideways motion. Now, let's move to something closer to our everyday experience. The International Space Station. The ISS orbits Earth at an altitude of about 400 kilometers, traveling at roughly 7.7 kilometers per second. That is about 28,000 kilometers per hour. At that speed, the station completes one full orbit every 90 minutes. The astronauts on board experience something that seems magical. They float, their food floats, their water forms perfect spheres that drift through the cabin. Their tools hover in midair. Everything inside the station behaves as though gravity has been switched off. But gravity has not been switched off. At 400 kilometers altitude, the gravitational pull of Earth is about 90% as strong as it is on the surface. The astronauts are absolutely experiencing gravity. Earth is pulling on them with nearly the same force you feel standing on the ground right now. So, why do they float? They float because they are falling. The station is falling toward Earth. The astronauts inside are falling toward Earth. Everything in the station is falling toward Earth. They're all falling together at the same rate, in the same direction. When everything around you is falling at the same rate you are, there is no relative motion between you and your surroundings. You don't press against the floor because the floor is falling away from you at exactly the same rate you're falling toward it. Your coffee doesn't stay in the mug because the mug is falling just as fast as the coffee. Everything is in free fall, And freefall feels like weightlessness. This is the same physics that governs planetary orbits, made tangible and visible inside a spacecraft. The station has enough sideways velocity that it keeps missing Earth. It falls and falls, but the Earth's surface curves away beneath it. The station traces a circular path around the planet, perpetually falling, never landing. And everyone inside experiences the physical sensation of that free fall as weightlessness. When you see footage of astronauts floating inside the station, performing somersaults, playing with floating water droplets, catching drifting tools, you are watching the visible consequence of orbital mechanics. You are watching what it looks like to fall around a planet. Every planetary orbit in the solar system involves the same free fall. The planets don't feel the sun's gravity as a sensation of being pulled. They are in free fall toward the sun, and free fall is indistinguishable from weightlessness. If you could somehow stand on a platform that moved with Earth through its orbit and block out all other forces, you would feel weightless in the direction of the sun. You would not feel pulled toward it. You would feel nothing, because you and everything around you would be falling toward the sun together at exactly the same rate. This insight has a deeper meaning in Einstein's framework. Einstein called it the equivalence principle. He realized that there is no way to distinguish between being in free fall in a gravitational field and being in empty space far from any gravity. The experience is identical. If you were in a sealed room with no windows, floating freely, you could not determine whether you were in orbit around a planet, falling toward a star, or drifting in deep space, a billion light years from anything. The experience of free fall is universal. It feels the same everywhere, in every gravitational field, at every scale. This is a profound statement about the nature of gravity. Gravity doesn't create a feeling of being pulled. Gravity creates curvature in space-time, and objects moving through that curvature follow curved paths. But the objects themselves don't feel the curvature. They are in free fall, and free fall feels like nothing at all. The only time you feel something is when something prevents you from falling freely. Right now, sitting or standing on Earth's surface, you feel gravity, but what you actually feel is the ground pushing up against you, preventing you from falling toward Earth's center. If the ground suddenly disappeared and you were falling freely, you would feel weightless, just like the astronauts. The sensation of weight is not caused by gravity. It is caused by whatever stops you from falling. Now, let's zoom out beyond the solar system and look at larger structures because the same principle applies everywhere. Stars orbit the centers of their galaxies. Our sun orbits the center of the Milky Way at a distance of about 26,000 light years. It moves at about 230 kilometers per second, and it takes approximately 225 million years to complete one orbit. This orbital period is sometimes called a galactic year or a cosmic year. In the entire history of the solar system, the Sun has completed only about 20 galactic orbits. The last time the Sun was at roughly this position in its orbit around the galaxy, dinosaurs were just beginning to appear on Earth. The orbit before that, the supercontinent Pangaea, was still intact. What keeps the Sun in this orbit? The same thing that keeps Earth in its orbit around the Sun. Gravity and sideways motion. The combined mass of everything closer to the galactic center. Hundreds of billions of stars, vast clouds of gas and dust, and an enormous amount of dark matter creates a gravitational pull that draws the Sun inward. But the Sun is also moving sideways, perpendicular to that pull, at 230 kilometers per second. That sideways velocity, combined with the inward gravitational acceleration, produces a curved orbital path around the galactic center. The Sun is falling toward the center of the Milky Way. It has been falling for billions of years, but it keeps missing because it's moving sideways fast enough. The same principle, the same physics, just operating on a vastly larger scale. And the Sun is not special in this regard. Every star in the Milky Way orbits the galactic center. Some are closer in, orbiting faster. Some are farther out, orbiting slower. The stars near the galactic center move at enormous speeds. There are stars within a few light years of Sagittarius A star, the supermassive black hole at the center of the Milky Way, that orbit at thousands of kilometers per second. One star, called S2, orbits the black hole once every 16 years at speeds reaching roughly 7,700 kilometers per second at its closest approach. That is about 2.5% of the speed of light. 2.5% might not sound like much, but that is nearly 28 million kilometers per hour, fast enough to travel from the Earth to the Moon in under 50 seconds. A journey that took the Apollo astronauts 3 days, this star completes in less than a minute. The black hole's gravity is so intense that anything moving slower would spiral in and be consumed. S2 survives only because it has enough sideways velocity to keep falling around the black hole rather than falling into it. Astronomers have tracked S2's orbit for over 20 years, watching it trace a clear elliptical path around the invisible black hole. This observation, made possible by infrared telescopes that can peer through the dust obscuring the galactic center, provided some of the strongest evidence for the existence of the supermassive black hole. The star's orbital motion revealed the black hole's mass, about 4 million times the mass of the Sun, compressed into a region smaller than our solar system. The rings of Saturn provide another beautiful example of orbital mechanics in action. Saturn's rings are not solid structures. They are made of countless individual particles, ranging in size from tiny grains of ice smaller than a grain of sand to chunks as large as houses. Each of these particles is independently orbiting Saturn. Each one is in free fall, falling toward Saturn while moving sideways fast enough to maintain its orbit. The particles closer to Saturn orbit faster. The particles farther from Saturn orbit slower. This differential speed is why the rings appear as distinct bands rather than a single solid sheet. The particles are all following the same laws of physics. The same combination of gravity and sideways motion, but at different distances and different speeds. From a distance, the collective effect of billions of orbiting particles creates the stunning visual spectacle of Saturn's rings, one of the most beautiful sights in the solar system. But up close, each particle is just a small chunk of ice or rock falling around a planet, obeying the same orbital mechanics as Earth orbiting the Sun. Moons throughout the solar system follow the same pattern. Jupiter has at least 95 known moons. Each one orbits Jupiter in free fall, pulled inward by Jupiter's gravity, moving sideways fast enough to avoid crashing into the planet. Io, the innermost of the 4 large Galilean moons, orbits so close to Jupiter that tidal forces from the planet's enormous gravity flex and squeeze the moon's interior, generating tremendous heat through friction. This tidal heating makes Io the most volcanically active body in the solar system, with hundreds of active volcanoes constantly resurfacing the moon. Io's orbit, its free fall around Jupiter, is what generates this volcanic activity. The orbit itself drives the geology. Europa, the next moon outward, also experiences tidal heating, though less intense than Io's. This heating is believed to maintain a liquid water ocean beneath Europa's icy surface. That ocean, kept liquid by the energy generated through orbital tidal interactions, is one of the most promising places to search for life beyond Earth. The possibility of life on Europa exists because of orbital mechanics, because of the physics of falling around a planet. Binary star systems offer yet another example. A large fraction of stars in the Milky Way exist in binary or multiple star systems. 2 or more stars orbiting a common center of mass. For Sun-like stars, roughly half are found in such pairings. For smaller red dwarfs, which make up the majority of all stars, the fraction is lower, perhaps 1 in 4. These stars are falling toward each other, pulled together by their mutual gravity, but moving sideways fast enough to keep missing. They trace elliptical orbits around a point in space between them, each one perpetually falling toward the other, each one perpetually missing. Some binary stars orbit each other in days, others take centuries or millennia. The physics is identical in every case. Gravity provides the inward pull. Sideways motion provides the forward component. The combination produces stable orbits that can last for billions of years. When we look at the largest structures in the universe, we find the same principle still at work, though the details become more complex. Galaxies orbit within galaxy clusters. The Milky Way and Andromeda, the 2 largest galaxies in the local group, are falling toward each other. Their mutual gravitational attraction has been pulling them together for billions of years. Currently about 2.5 million light-years apart, they are approaching each other at roughly 110 kilometers per second. In about 4.5 billion years, they will merge. But even this motion is governed by the same physics. The 2 galaxies are falling toward each other through curved spacetime, each one's path bent by the other's gravity. Galaxy clusters themselves move within superclusters. The Milky Way, along with the rest of the local group and thousands of other galaxies, is falling toward a concentration of mass called the Great Attractor, drawn by the combined gravity of enormous structures hundreds of millions of light years away. Everything is falling toward everything else. The entire cosmos is a vast web of gravitational interactions, with objects at every scale falling toward other objects, moving sideways, tracing paths through the curved space-time created by the distribution of mass and energy throughout the universe. This is the picture that emerges when you truly understand why planets don't fall into the sun. It's not just a story about 8 planets and 1 star. It's a story about the fundamental nature of motion in a universe governed by gravity. Everything falls, everything moves. The combination of falling and moving produces the orbits, trajectories, spirals, and paths that give the universe its structure. Without this mechanism, the universe would look completely different. If objects only fell straight toward each other with no sideways motion, everything would simply collapse. Every cloud of gas would collapse into a single point. Every star would fall into the nearest black hole. Every galaxy would shrink to nothing. The universe would be a formless soup of matter, collapsed into dense clumps with nothing orbiting anything. But that's not what happened. Because the original material of the universe had motion. The clouds of gas that formed stars and galaxies were rotating, swirling, and moving in complex patterns. This motion was preserved as the clouds collapsed, amplified by the conservation of angular momentum, and converted into the orbital motions we see today. Every orbit in the universe traces its origin back to the motion of the primordial gas, from which the orbiting objects formed. The rotation of the original cloud becomes the revolution of the planets. The swirl of a collapsing gas cloud becomes the spin of a galaxy. Motion is not something added to the universe, it is intrinsic to it. The universe was born moving, and it has never stopped. Let me leave you with something to think about the next time you look up at the sky. You are standing on a planet that is falling toward the sun at this very moment. You have been falling toward the sun your entire life. Every person who has ever lived has spent their entire existence falling toward the sun. But we've never gotten any closer because we're also moving sideways at 30 kilometers per second. And that sideways motion means we keep missing. The moon above you is falling toward Earth. The stars you see scattered across the darkness are falling toward the center of the galaxy. The galaxy itself is falling toward the Great Attractor. Everything is falling. And that falling, that universal, perpetual, inescapable surrender to gravity is not a catastrophe. It is the organizing principle of the cosmos. There is something deeply beautiful about this. The planets don't orbit because they resist gravity, they orbit because they surrender to it completely. They fall freely, without fighting, without pushing back, without any force opposing the pull. And paradoxically, that total surrender to gravity is exactly what prevents them from crashing. By falling freely, by giving into gravity entirely while carrying their sideways motion with them, the planets trace paths that loop around the sun and bring them back to where they started. Over and over, endlessly. Free fall is not destruction. Free fall is a structure. Free fall is orbits and rings and moons and galaxies. Free fall is the architecture of the universe. Everything you see when you look up at the night sky, every star, every planet, every galaxy is held in place by objects falling towards each other and missing. The entire visible universe is an elaborate dance of things falling and missing for billions of years. Newton saw this. He understood that the apple and the moon were governed by the same force, that falling straight down and orbiting were two versions of the same phenomenon. Einstein saw it more deeply. He understood that gravity isn't even a force, that free fall is the natural state of motion in curved space-time, that orbiting objects are moving as straight as possible through a universe whose geometry is bent by mass. Both of them, separated by more than 2 centuries, grasp the same essential truth. The universe is in free fall, everything falls, and from that falling comes everything we see. The next time you watch the sunset, remember what is actually happening. The sun isn't moving across your sky. You are. You are on a planet that is rotating on its axis while simultaneously falling around the sun at 67,000 miles per hour. The sunset you're watching is caused by your motion, not the sun's. You are spinning away from the sun as Earth rotates, and you interpret this as the sun going down, but really you are the one moving. You're riding on a falling planet, spinning on its axis, hurtling through space. The sunset is a consequence of orbital mechanics, of the same physics we've been discussing all evening. And it is beautiful. Not despite being physics, but because of it. Understanding the mechanics doesn't diminish the beauty. It deepens it. Knowing that the sunset happens because you are on a planet that has been falling around a star for 4.5 billion years. That the colors come from sunlight scattered through an atmosphere held in place by gravity. That the entire scene is made possible by the precise balance of sideways motion and gravitational pull that has persisted since before the Earth had oceans or continents or life, Knowing all of that makes the sunset more wondrous, not less. So why don't planets fall into the sun? Because they are falling into the sun. They always have been. They just keep missing. And they will keep missing for billions of years more, tracing their ancient path through curved spacetime, falling freely, moving forward, turning endlessly around a star that holds them not by gripping them in place, but by bending the space through which they travel. This is the answer, not a force pushing outward, not a balance of competing pulls, just falling and moving, gravity and motion. The simplest ingredients producing the grandest result. The entire cosmos structured by objects that fall toward each other and never quite arrive. The universe doesn't need anything complicated to hold itself together. It doesn't need invisible barriers or mysterious repulsions or divine hands arranging the planets in their courses. It needs only two things: mass that curves, space-time, and objects that move through that curved space-time. From these two ingredients, everything follows. Orbits, rings, moons, solar systems, galaxies, galaxy clusters, the cosmic web itself. All of it emerges from the interaction of gravity and motion, from the endless falling of matter through the curved geometry of space-time. There is perhaps no better demonstration that the universe is both simpler and more elegant than we tend to imagine. We look at the night sky and see complexity. We see planets in different orbits at different speeds, moons circling planets, rings encircling worlds, stars wheeling through the galaxy. It looks complicated. It looks like it must require elaborate explanations with many moving parts, but it doesn't. It requires one force, gravity, and one property of matter, inertia. And from these two alone, all the orbital complexity of the cosmos emerges naturally, inevitably, beautifully. The planets don't fall into the sun for the same reason the moon doesn't fall to Earth, for the same reason the space station floats, for the same reason stars orbit black holes, and for the same reason galaxies don't collapse. Everything is falling. Everything is moving. And the combination of falling and moving, repeated at every scale from moons to galaxy clusters, is the heartbeat of the universe. You are part of this. You are on a falling planet, orbiting a star, in a galaxy that is itself falling through the cosmos. Every atom in your body is participating in this universal free fall. You are, quite literally, made of matter that has been falling through space for billions of years. And you will keep falling, along with your planet and your star and your galaxy, for billions of years more. You don't feel it. You can't sense it. But it is the most fundamental motion of your existence. You are falling right now. You have always been falling, and you always will be. But you will never arrive. None of us will. And that is the most beautiful thing about the cosmos. The falling never ends. The dance never stops. The planets keep circling. The stars keep orbiting. The galaxies keep turning. All of it sustained by the simplest principle in physics. Matter falling through curved space and missing what it falls toward, over and over again, forever. That is why planets don't fall into the sun. And that is why the universe looks the way it does. Thank you for joining me on this journey. If you found this exploration valuable, a like or a subscribe would mean a lot. It helps me keep making these deep explorations of how the universe works. And the next time you look up at the sky and see the moon hanging there, or a planet glowing steadily among the stars, remember what you now know. Those objects are falling. They have always been falling. And they will keep falling and missing for longer than you or I or anyone can imagine. That is the secret of the cosmos. Not resistance, not balanced, just falling. Endlessly, gracefully, perfectly, falling. Good night. And may you never look at an orbit the same way again.